All right, well, thanks to all of you for coming out for this event. It's a real pleasure to be here in Iceland. I love making it out to this part of the world. It's a beautiful country. The climate is cold, but the people are warm, and I always enjoy the time that I spend here. And I'm especially pleased to be participating in this extremely important event that Gudni has organized to share with you really pretty much everything that we know about the issue of human-caused climate change. So what I'm going to do with this lecture is provide an overview of the topic of climate change, the scientific evidence that is happening, that is caused by human activity, the predictions for the future and what the likely impacts will be, and of course the solutions. What can we do about this problem? And the good news is that we still can do something about this problem. The first point that I'll make is that the science is actually very straightforward. Climate change is often presented as a contentious issue, as if there is a debate within the scientific community, when in actuality there is an overwhelming consensus about the basic science. And some of it is pretty simple. It's chemistry and physics that goes back nearly 2 centuries, the greenhouse effect. We've known about the greenhouse effect for nearly 2 centuries. Joseph Fourier. You have to go far enough back that there aren't even photographs of the first person who was aware, the first scientist who was aware of the greenhouse effect, Joseph Fourier, who gave us the law of heat conduction back in the early 1800s. He understood that certain gases in the atmosphere, what we call greenhouse gases, have this warming influence on the planet. And it is incontrovertible that we are increasing the concentrations of these gases. In fact, this graph here that I constructed a few years ago is already fundamentally out of date because you have to add another vertical tick mark to the scale. We crossed 400 parts per million CO2 in the atmosphere for the first time 4 years ago. For the first time in what we are fairly certain is millions of years. So we are engaged in this unprecedented and uncontrolled experiment with the one planet that we have. Okay, now, as I said, this is basic physics and chemistry that goes back nearly 2 centuries, irrefutable measurements that we are increasing the concentrations of these greenhouse gases. What I would not be able to explain to you as a scientist would be if the Earth were not warming up. It has to warm up based on everything we understand about the underlying science. And of course, it is warming up. The globe has warmed a little less than 1 degree Celsius over the past century. Now, if you're a critic, and yes, there are critics when it comes to the science of climate change, there are some of them here in Iceland, and they'll look at a graph like that and they'll sort of cherry pick their starting date. They'll say, well, look, it was really warm there, and in 2012 it wasn't so warm, so maybe global warming has stopped, right? There's a pause in warming. Well, that's not how we measure trends scientifically, but the easiest response to that sort of argument is simply to update the graph. So let's update that graph. It ended actually in 2013. Here's 2014, the warmest year on record. So let's add 2014. Unfortunately for 2014, its title as warmest year on record was short-lived. It lost out in just 1 year to 2015, which became the new warmest year on record. And that's what the graph looks like when you add 2015. Now, I have some bad news for 2015. It is going to lose its title because based on just the 4 months of data we already have for 2016, which places us somewhere up there, we are now about 99% confident, even with 4 months of data, only 4 months of data in, that 2016 will be the warmest year on record. So we've broken the record for warmest year 3 times in a row consecutively. We've never seen that before. Or that will have been true, I argue, by the end of 2016. Now, the critics will tell you they don't trust those thermometer measurements. Well, let's throw out all the thermometer measurements. I could literally show you dozens of independent lines of evidence from various sources that tell us an internally consistent story of a planet that is warming and a climate that is changing, much as we expect it to, as we continue to increase the concentrations of these gases. And that's the sort of evidence that has led the very conservative Intergovernmental Panel on Climate Change, the IPCC, which consists of hundreds of scientists from around the world and putting out reports every 5 to 6 years that reflect the current state of understanding of the science of climate change. Now, these reports are sort of a lowest common denominator. They represent the conclusions that a large number of scientists can all agree upon. So by their nature, they tend to be very conservative assessments. And that means that when the IPCC says that the warming of the climate system is unequivocal, what that means is that the warming of the climate system is unequivocal. Scientists aren't debating that fact. Now, none of that is based on climate models. Another thing you'll sometimes hear from the contrarians in the climate change debate is that our entire understanding about climate change is based on these unreliable models. Well, that's doubly wrong because it's not based on the models. I already showed you the evidence that human-caused climate change is real, and it wasn't based on climate models. And the models aren't unreliable. Now, in fact, they have been able to reproduce the observations with remarkable skill. Now, this is the observed temperature record. And what we can do is we can take those climate models and we can drive them with just the natural factors. Because if you're a critic, if you're a skeptic, a pseudo-skeptic, I would say, a fake skeptic, you might say, well, so it's warmed. How do we know it isn't due to natural causes, like volcanic eruptions that come and go, changes in the brightness of the sun? These natural drivers can obviously cause temperatures to fluctuate. Maybe it's those natural factors. Well, we can take the climate models, we can put the natural factors in there, and that's what they predict. They predict that the climate should have actually cooled over the latter half of the 20th century because we've had a number of large cooling volcanic eruptions. Solar output has been flat or even slightly on the decline. When you just put the natural factors into the models, you can't reproduce the observations. Now, when you add the human factor of increasing greenhouse gas concentrations from fossil fuel burning and other human activities, we actually reproduce the observations remarkably well. And that's the sort of evidence that has led, again, the very conservative IPCC to state that it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. Now, the IPCC hates to use terms like extremely likely. It's an extremely conservative group. To say that something's extremely likely, the evidence has to be extremely strong. And even here in this statement, the IPCC betrays its intrinsic conservativeness, its intrinsic scientific reticence. Because if you read the technical chapters of the report, what you will find is that it is most likely the case that human activity is responsible for more than 100% of the warming that we've seen. How can that be, you ask? What do you mean by that? Well, you've already seen why that's the case. Natural factors were actually pushing us in the opposite direction, towards cooling, and we warmed in spite of that. Now, we do use these models to make projections about the future. As Niels Bohr once famously said, the great physicist Niels Bohr, predictions are hard, especially about the future. It's supposed to be funny. Niels Bohr actually did say that. Americans tend to think that it was Yogi Berra who said that because he said all these funny things. It was actually Niels Bohr, the physicist. And we can make, as you've seen, the models can actually reproduce the observations. The models have made impressive predictions. And we can make projections forward. But the problem is we don't know what we're going to do. The one thing we can't predict at this point with any degree of certainty is what we human beings will choose to do. Will we choose to basically curtail our burning of fossil fuels immediately? Well, if we could do that, we would avoid crossing this critical threshold of 2 degrees Celsius warming relative to pre-industrial. That's the amount of warming, as we'll see, where we really start to see some of the worst impacts of climate change. We could avoid warming the planet by that amount if we were to take action immediately. On the other hand, if we continue with business as usual burning of fossil fuels over the next century, we'll be somewhere up in this range of about 4 to 5 degrees Celsius warming of the planet. When I'm in the United States, I'll do the translation to Fahrenheit, 7 to 9 degrees Fahrenheit. twice that much warming in the Arctic because of the amplifying effect of the disappearance of sea ice and the increased warming of the Arctic Ocean that results from that. Now, we can actually look at one of these climate models, and we're literally watching it go forward on a seasonal basis, and we're looking at where it's warmer than the 20th century average and where it's cooler than the late 20th century average. We're in the past at this point. Here's the global average temperature. That's the red trace. We're now nearing 2000. Pretty soon, we will be into the future. Now we're going into the future. And yes, there will be years where it will still be cold in the winter in North America. Cold winters will still happen, and they don't disprove global warming. Iceland, again, gets cold winters, gets warm winters. As time goes on, what you see is the cold gets less and less widespread. The warming gets more and more widespread. Pretty soon it becomes pervasive. You can see that enhanced warming in the Arctic because of the amplifying effect of losing that sea ice. You get even more warming in that region. You can see El Nino events coming and going. These models really capture a lot of the dynamics that we see in the actual climate system. They've become quite reliable, quite impressive in their ability to reproduce nature. Now, at this point, you're probably noticing there is one thing that sticks out here like a sore thumb. And I'll see if I can stop it. And really, let's see if we can. Oops. So we have the enhanced Arctic warming, but there's this region, this blob, this blue blob in the North Atlantic coming very close to Iceland, in fact, at times expanding into Iceland. You might ask, is that an error in the model? Is there a bug in the model? Is something going wrong? No. As we'll see later on, not only do the models predict this to happen over the next 1 to 2 centuries, we think that we're seeing this happening now, ahead of schedule. And this will be a recurring theme. There are things that are happening now that are happening ahead of schedule relative to what the models predicted. Now, it isn't just temperature we care about. We care about water. We, human beings, other living things, rely upon fresh water to live. And what the models tell us is that there will be large changes in the amount of precipitation. In the tropics, we'll actually get more precipitation because a warmer atmosphere holds more moisture. You'll still have that rising motion that happens within the tropics, and where you have rising motion and you have moisture, you get rainfall. In the subtropical latitudes and into the middle latitudes, into North America, for example, where I live, the models indicate that the sinking dry air that we typically find in the belt of deserts today, in the subtropics, somewhere around 30 degrees north and south, that sinking air will actually expand poleward. And so we will get more desert-like conditions over large parts of Europe in the summer, over large parts of North America. Then once you get into the higher latitudes, the jet stream is going to move north. Those storms are going to move north. We're going to have rising motion within those storms, a warmer atmosphere. So yes, we'll get more rainfall once again. So you might look at a picture like that and say, well, the challenge then globally is just to move the water around. It's a zero-sum game. Some regions get more rainfall, other regions get less. We could just build huge pipelines to move the water around from where there's an excess, where there's a surplus, to where there's a deficit. Unfortunately, it doesn't work that simply, because what we see at the surface where we live, we rely upon for agriculture, is the soil moisture. It's how much moisture is in the soil, which isn't just how much rainfall is coming down, it's also how much moisture are we losing to the atmosphere through evaporation. Now remember, the planet is warming up, and one of the simplest relationships in all of meteorology is as you warm up temperatures, you get higher rates of evaporation. You lose more of that moisture into the atmosphere. And so that's what rainfall changes look like, but that's what drought looks like. Worse drought over just about all of the world's continents, because even in regions that get more rainfall, in many cases, oops, didn't mean to do that, they lose more moisture due to evaporation. So drought becomes more widespread, more pervasive. Arctic sea ice, another example of, again, a recurring theme that you will see here. The gray shaded region is what the models predict, what the IPCC models predict. The red curve is what's actually happening with respect to Arctic sea ice, the decline in Arctic sea ice. The models say, well, you know what? It'll take until the end of the century until we have any chance of seeing ice-free conditions in the Arctic. But the observations seem to be indicating otherwise. They are way outside the envelope of uncertainty of the model predictions. And by the way, 2016 right now is somewhere down here. We're probably going to set a new record low in Arctic sea ice this year. Now, it's instructive to actually look at what that looks like spatially. Let's actually watch the Arctic sea ice evolve from season to season over the last few decades due to this wonderful animation from NASA. The white ice is going to be the old, very thick ice, multi-year ice. It's very robust. It's very thick. The bluer the ice gets, the thinner it is, and the more likely it is to be just seasonal ice. Ice that melts in the summer, comes back in the winter. It's not persistent. It doesn't last through the summer. And we're watching time go on, 1998, 1999. You should notice the sea ice is getting less and less, especially that multi-year thick ice, the good ice if you're a polar bear. The ice that you want is getting quite a bit less in extent. We'll look at 2007, what happened there. Now look at 2012. We have essentially no multi-year ice left. Essentially all we have now is the seasonal ice that comes in the winter and it's lost in the summer. And we're now ahead of where we've ever been in terms of how much ice we've already lost this season. Well, that's sea ice. The good news about the loss of sea ice is that it doesn't contribute to sea level rise because that ice is already floating on the water. You melt it, it doesn't make the sea level higher. You lose land ice, it makes the sea level higher. Greenland, that red here shows what we saw in 2012. We didn't expect to see this for decades, but we saw it in 2012. There was melt taking place across the entire Greenland ice sheet. It doesn't mean it's lost its ice. It means it is melting at the surface now, everywhere over the surface of Greenland. We saw that for the first time in 2012. Ahead of schedule. The loss of the Greenland ice is ahead of schedule. The loss of Antarctic ice is ahead of schedule. We're losing ice from these ice sheets decades ahead of when the models said that this should be starting to happen. That means that we are ahead of schedule with respect to our projections of future sea level rise. Sea level rise is happening now faster than we expected because we're losing the ice, the land ice, faster than we expected. All right, recurring theme. Climate scientists like myself, like Stefan Rahmstorf, we're often accused of being alarmists for overstating the evidence. The sad fact is, if anything, we as a community have been too conservative. Our model projections have underestimated the rate at which the changes in climate are now occurring. Now, one of the things we worry about are so-called tipping points. And there's no one tipping point in the climate system. People sometimes ask me, what's the tipping point? What's the amount, where we go past the point of no return? There's no one tipping point. There are many tipping points. Some of them we've probably crossed. We've probably warmed the Earth enough that we will lose the entire or most of the West Antarctic ice sheet, no matter what we do, enough to get 10 to 14 feet of additional sea level rise. We can't stop it from happening. Even if we could magically turn the thermostat back down, bring Earth's temperature back down, once you set that in motion, it gains momentum and you can't stop it from continuing. That's what we call a tipping point. You can't go back. We think that the loss of ice from the ice sheets is an example of the tipping point. Another tipping point you'll hear more about is the potential collapse of the so-called conveyor belt ocean circulation pattern that brings warm water northward and warms Iceland and warms other regions neighboring the North Atlantic to the point where they're more moderate, they're warmer in their climate than they would otherwise be in the absence of this particular ocean circulation pattern. And we now understand the physics of the way this ocean circulation pattern works is such that it can collapse suddenly. It doesn't just have to change slowly. As we warm the planet, as we melt ice and fresh water runs into the North Atlantic and makes that water lighter and inhibits the sinking motion in the North Atlantic that drives this conveyor belt ocean circulation pattern, that change can happen abruptly. Now, it can't happen in 3 days, which was what is envisioned in the movie The Day After Tomorrow, where this scenario literally plays out over a course of 3 days or 4 days, and we form entire ice sheets over the northern hemisphere over the course of 3 or 4 days. That's, of course, a caricature of what the science has to say. But the grain of truth in the movie The Day After Tomorrow is that these changes can happen abruptly when we're talking about climatic timescales as short as a decade or so. And so much of what's happens in the movie The Day After Tomorrow is unlikely to happen, but the grain of truth that this ocean circulation pattern could slow down because of global warming, not only do we think it's credible, we think it's happening. We think it's happening ahead of schedule. Stefan Rahmstorf, my colleague here, and I co-authored. Stefan was the principal author on an article in the journal Nature Climate Change last year that showed that while the climate models predict that this ocean circulation pattern shouldn't really start to slow down until the 21st century, until the century that we're in, the observations appear to suggest that it has slowed substantially over the last century, that we're already seeing the slowdown of the conveyor belt ocean circulation pattern. The source of the cool blob, the cold blob in the North Atlantic that we saw in that climate model simulation that happens 100 or 200 years from now, if you look at the observations, it's happening now. That's what the 2015 global temperature pattern looked like. The warmest year on record for the world's oceans. Record temperatures over just about the entire surface of the world's oceans, except for this region, south of Iceland, neighboring Iceland in the North Atlantic, where we saw the coldest temperatures on record during a year that saw the warmest temperatures on record globally. So we're fairly certain that we are actually seeing the slowdown of this current play out ahead of schedule. And there are potential implications, of course, in that for Iceland. So what about the implications of the projected temperature changes if we do proceed with business as usual, burning of fossil fuels, and we warm the planet 4 to 5 degrees Celsius by the end of the century, as famous climate scientist colleague of ours, James Hansen, has put it, we'll be talking about a different world, a different planet. It won't be the planet that we grew up on. Now, it used to be that I would show a sequence of images, and I would end with this photo here because it's actually the law in the United States. If you're giving a talk about climate change, you have to show a polar bear stranded on an ice floe. But seriously, by making the polar bear the poster child of climate change, and by the way, here in Iceland, you can actually see polar bears, occasionally at least, as I understand it. We don't have them back in the United States. The only place you can see them is at the zoo. And because of that, when you show the polar bear and you make it the poster child of climate change, it communicates the notion to most people that this is an exotic, far-off problem. Maybe it's a problem for polar bears up in the Arctic, but it's not a problem for me, right? So everywhere I go now, I try to find local examples of how climate change is impacting us now where we live in negative ways, in bad ways. And it is disturbingly easy to do that everywhere I go. Whether it's Central Texas, I gave a talk there, used this image that I'd found on the internet, not realizing that it was from their town. It was from San Angelo, Texas. It was what they used to call Fisher Lake. And that lake disappeared in the 2011 unprecedented Texas drought. Or I gave a talk in the UK where the flooding they had last winter the very conservative scientists of the UK Met Office, and you can't find more conservative scientists than the scientists at the UK Meteorological Office. And when they said that the flooding that they saw wouldn't have happened in the absence of human-caused climate change, that the flooding wouldn't have been as bad, it wouldn't have been the record flooding that they saw in the absence of the warming of the globe, you can be fairly certain that that's the case. California, worst drought. It's still in the midst of the worst drought on record. And when I say on record, the paleoclimate scientists tell us at least 1,200 years. This appears to be the worst drought in at least 1,200 years. Now, I personally think that's unlikely to be a coincidence. Some scientists say we can't link this drought definitively to climate change. But it turns out more than 10 years ago, scientists were already saying that there's something very interesting that happens when you lose Arctic sea ice. You actually change the pattern of the Northern Hemisphere jet stream. And you change the pattern of the Northern Hemisphere jet stream in a way that causes it to veer north of California in the winter. And you get worse drought. You get less precipitation. You get less snowpack. That appears to be happening. And that probably is contributing to the fact that California has had the worst drought on record. Of course, it doesn't help that they also saw the warmest temperatures they've ever seen last year, which means there was more evaporation as well. And by the way, the governor of California, who has been very active in trying to implement policy to deal with climate change, let me just say he knows where to get his climate information. So. Florida, where there's this recurrent seasonal flooding. They call it the king tide. It happens several times a year. It's a natural phenomenon. But what isn't a natural phenomenon is what's happening now, where every time it arrives, there's widespread flooding of Miami Beach and of Fort Lauderdale and of an increasingly larger part of Florida. And that's the way we are going to see the impacts of sea level rise. It isn't just going to be some very slow, gradual inundation. The extreme events are going to become more extreme. And events where we might have been able to mitigate the impacts of the flooding through dikes, through levees, the flooding will be such that we will no longer be able to implement adaptive measures. We will literally need to retreat from our coastlines. A similar thing with New York City, combination of global sea level rise and a very unusual superstorm, Sandy, largest storm on record, tropical storm in the North Atlantic on record. The lowest central pressure, one measure of the intensity of the storm, of any North Atlantic tropical storm that ever made it north of Cape Hatteras, North Carolina, took a very unusual trajectory, went towards the East Coast rather than out to sea. That was tied to the unusual pattern of the jet stream, which, yes, is the pattern of the jet stream that scientists say is becoming more frequent because of the loss of Arctic sea ice. Forget all of that. Just the fact that there was 1 foot of global sea level rise, and we know that that's caused substantially by climate change, human-caused climate change, means that if you estimate the likelihood of a 14-foot storm surge like they saw in Battery Park, New York City, that should only be a 1-in-a-century event. And we've seen it once this century. We saw it with Superstorm Sandy. If we continue with business as usual, fossil fuel burning, by the end of the century, that becomes a 3 to 4 year event. A Hurricane Sandy-like storm impacting New York City and the New Jersey coastline every 3 to 4 years. At that point, there is no degree of adaptation that saves New York City. We are once again talking about literally retreating from our coastlines. Now, there's actually a song that I found on the internet called Tropical Iceland. And everywhere I go, as I said, I see evidence that climate change is a pretty bad thing. It's impacting us negatively. This is the first place I've been where, frankly, climate change might be a good thing for you folks. Not really. It won't give you palm trees. It might mean temperatures are warmer and more moderate, but there are all sorts of potential surprises that loom in our future. And one of them relates to that Atlantic conveyor belt ocean circulation pattern. If indeed we are already seeing a dramatic slowing of that ocean circulation pattern, it could have huge impacts for Iceland. It could actually mean colder extremes, but being intermittent with summers that are warmer, so larger fluctuations, more extreme temperatures. It's difficult at this point to actually predict what the impacts will be on Iceland from the combined effect of global warming and the possible slowdown of this ocean circulation pattern. But one thing we do know is that this ocean circulation pattern is actually critical for maintaining the nutrients in the ecosystem of the North Atlantic that makes it such a productive region for marine fisheries. And of course, here in Iceland, we have, as I understand it, the only sustainable cod population in the world now. And if we see a slowdown of this current system, that could have dire implications for fisheries here in Iceland and for the entire world. And Iceland is indeed, at least at the periphery of the cold blob, at least at times when the cold blob expands, it does seem to move into the region, the vicinity of Iceland. So we've seen the evidence that climate change is real, it's caused by human activity, and it's a problem. Not just a problem in the future, it's a problem now. And it's a problem that we, I think, all can agree we ought to try to do something about. There really are very few things that we can do to adapt to the kinds of changes that will be in store if we warm the planet 4 to 5 degrees Celsius by the end of the century. In the short term, there are things we can do with our water management, our agriculture, ways of adapting to modest changes in sea level, increases in sea level. For small amounts of warming, if we can keep warming below 2 degrees Celsius, we can probably meaningfully adapt to the changes that will be in store. But if we continue with business as usual burning of fossil fuels, and we get 4 to 5 degrees Celsius warming of the planet by the end of this century, and more to come thereafter, there are no reasonable scenarios where we can adapt, where that sort of change is within our adaptive capacity, let alone the adaptive capacity of every other living thing on the face of the earth. And that leaves only one possibility, that we engage in a massive scheme to interfere with Earth's climate in other ways to offset global warming. No, I'm just kidding. That would be a very bad idea. But there are serious scientists out there who say, well, maybe we can do that. Maybe we can do other things to the planet to offset global warming, like shooting huge amounts of particles, like what a volcano does, into the stratosphere, but doing it every, 1 or 2 or 3 years, often enough that we offset much of the warming of the planet. Now, if you do the calculations, yeah, in principle we could do that, but the pattern of the cooling from the aerosols doesn't look like the mirror image of the warming from greenhouse gases, so some regions would warm even faster, including maybe the region where the ice sheets are located. Other regions could cool. The land regions will actually dry out in that scenario. So drought will get even worse, acid rain will get worse, and ozone depletion will get worse. And every one of these schemes comes attached to a whole set of potential unintended consequences. So I don't think geoengineering is a valid solution to this problem. That leaves only one other solution, which is us doing something about our ongoing burning of carbon and the ongoing increase in carbon dioxide concentrations from human activity. If you've got a 30 metric ton carbon footprint, which is what a typical American has, there are lots of things you can do to bring it down to a much smaller 4 metric ton carbon footprint. I think Iceland's, the average Icelander has a carbon footprint somewhere in the range of 14 tons per person. There are all sorts of things that we can do that make us healthier, that save us money, and they reduce our carbon footprint. And we ought to be doing those things. But just doing those voluntary actions, engaging in voluntary measures alone, isn't going to be enough to prevent us from warming the planet more than that critical 2 degrees Celsius amount of warming. If we're going to do that, we're going to need policies that incentivize the necessary transition away from fossil fuels towards other non-carbon-based forms of energy. And there's a worthy debate for us to have about how we do that, how we accomplish that transition. And there is room at the table for conservatives and progressives in debating those solutions. What we can no longer debate meaningfully, in good faith, is that the problem exists. And I will leave it there. Thank you.